In this video, we'll move into chapter 2, 2.1, which finally introduces our major concept, the idea of the derivative. This will be the last section that's included on our first test. We'll have a separate little review video, but those topics on our first test will have all the concepts with limits, the ideas from continuity, and now just this section on the definition of the derivative. And this, for some of you who are still a little up in the air, not quite sure where things were going in section 1.4 when we started, this is where it all starts to come back together. Now, there are still several major ideas that go along with the derivative, little things that we want to keep in mind. Sometimes they're a little bit more than little. So we've got a lot to cover here, but the big issue is this idea of the definition. And all of this comes back to that idea, slope of the tangent line. So we're going to start by revisiting this. That will lead us to this definition. When we get there, not to jump too far ahead, but that is going to be our definition. That concept of the derivative is going to be the function that gives us the slope of the tangent line to a curve at any point. So, first things first, getting into our picture. So again, just to remind us where we were, here is some function, f of x. Let's focus on some particular x coordinate a. And let me just draw a little simple picture here. So let's just do something like that. So with this coordinate a, that would lead to this point, which would very roughly lead to this as the tangent line. And we are trying to figure out the slope of this tangent line. One very quick thing to mention, a couple of you brought this up when we had the 1.4 video. If we want the slope of the tangent line, why don't we just pick another point on here and use our traditional slope formula? That is an excellent observation, everybody. But just to realize, the issue is I'm roughly drawing this tangent line. I don't have the ability to make it perfect. Maybe I'm slightly off. If we wanted to approximate the slope, that suggestion would be perfect. Even with a rough scale on this graph, all those little things, we could still do a decent job approximating. But what we are trying to do is to make this perfect, and not just for the situations where we have the graph. Even though we're looking at a graph, we're actually working towards a formula that we'll use for equations. Okay, so that is where we start. That is what we are ultimately looking for. But to realize, the curve is all we really know about. So how can I use the curve to get a decent approximation for the slope of this tangent line? So ultimately, again, slope of the tangent line, that is what we are searching for. But what I'm going to do is I'm going to apply the secant line. I'm going to use 2 points. So I'm just going to have our little y2 minus y1 over x2 minus x1. Since we know this is a function, I could instead write this f of x2 minus f sub x1, f of x1. That would be the equivalent. The y value at x2 is the same as y2, just some slightly different notation. But again, the issue is I don't have a second point. So I'll use the curve for a second point. If I pick my second point to say right about here, so this would be the x coordinate, and then I'll still change color, so I'll use my red pen to connect these 2 points. And like we saw in 1.4, that red line is not a good approximate, but it can kind of give us the slope of this original tangent line. Again, maybe this is about -2 and this is -3, just at this first point, but they're both negative. They both kind of have that same orientation. But at this stage, this is a terrible approximate, but we can do better. But before I get too hung up, I want us to start getting a little bit further with the notation. Instead of having this as x1 and this as x sub 2, we're going to leave a as the point we really care about. The slope of the tangent line to the curve at the coordinate x equals a. We're going to build on that. So I've got my a established. And since we kind of already know from 1.4, the way to get this secant line to be a better representation of this tangent line is to pick that second point closer. So instead of just calling this second point x sub 2, I'm going to call it a plus h, where h is going to be used as the distance we're moving away from the original a. So maybe in this first one, if this is the x-coordinate 2 and this is the x-coordinate 3, h would be 1. I've picked this second point 1 unit of distance away from the first. Now, by making that little adjustment, this is still the slope of a secant line, but now I could rearrange this a little bit. That my top, instead of f of x2, this will be f of a plus h, that having the original x-coordinate a and adding that value h gives you a new x-coordinate, and this represents the y value at that x-coordinate, minus the y value at the original x, so that'll be f of a, all over x sub 2 minus x sub 1, so that'll be a plus h minus a. And now we'll notice, you may ask, why am I changing the notation? What's the purpose here? Well, this is our first purpose right here, that these a values would cancel, and that we've simplified this formula a little bit, that now we're focusing on the x-coordinate a, h is the distance we're moving away, and it's just some slight change in our notation. But now, as we've seen, and as we've already quickly discussed here, that initial red line I drew is not really a good representation for the original tangent line. So how can I do a better job? Pick a closer point. So now if I pick this as my second point, now this smaller distance would be my h, and this would still be a plus h following this same notation. So this would still represent the slope, but now when you focus on these 2 points up here, and when I draw my red line, much, much closer. This red line is so much closer, especially if I draw it a little further, it will crisscross up here. But that red line is so much closer to my original tangent line than that first red line was. How did I make it a better approximate? I picked my second point closer to my first. So in terms of h is a smaller value. And how does this get better? This will continually get better the closer we pick our second point, so the smaller the value of h that we allow. Now I'm drawing all my h's to the right with h being a positive. This would work if h was a negative and I could have my second points over here, but I'll just keep working on the right side, that if I pick my second point right here, that would be right here, tangent line, second point right here, which makes that the point, second x right here, that would make that the point. And now at this point, my 2 points are almost right on top of each other. So my secant line here is really the same as that original tangent line that we drew. So what have we done to this formula? Again, every secant line, whether it's the first secant line with this as the second point, the second secant line with this as the second point, the third, the fourth, all these secant lines, their slope could be represented by this. But how do we make this into the tangent? What's the extra component? It's all about h. And what we are seeing is, again, the smaller the value h, the closer these 2 points are to each other, and the better representation for the tangent line. So how do I let h continue to get smaller and smaller? That is the limit idea. We are doing this idea, but we are taking the limit as h approaches 0 of f of a plus h minus f of a all over h. That That is what we call the definition of the derivative. I know that seems a little strange. Why do we call it the definition? It looks more like a formula, but that even though it is, right? Essentially, it is a formula, and we're going to use this formula to get these slopes of tangent lines, to get these values of the derivative. But, again, we're going to start slow. We're going to just take it easy with this first concept. But overall, that's where we're going. And what I also wanted to say was, even though that seems strange, that's how math works, right? Sometimes, even though it's a formula, that formula comes from all these concepts, and that's why it satisfies this idea of a definition. So just a little bit more. Here, we're just using that generic m for slope, and I'm subscripting tangent. But let's be even more specific. This is, again, the slope of the tangent line to a function f of x at the x coordinate equal to a. Notation, this would be, if the original function is f of x, we use this little prime, f prime of a, and that is the shortcut. That is the notation for the derivative. If the original function was g of x, then its derivative would be g prime of x. I'll come back to the x notation in a moment. Just for right now, just trying to establish that little prime, that little extra mark next to your original function is your notation, is your indicator that you're looking at the derivative and not the original. Okay, so we've got the idea established. We've got a lot more reminders that we want to say, and we have a lot more practice that we want to get. But now we've formally established the definition. We've answered the tangent line problem that we started in section 1.4. Again, we still have a lot more we want to add to it, but at least we've got the idea. We had concepts of slope. We saw the direction we were going, but we formally needed to understand limits to make that connection, and how secants can lead us to tangents. Okay, so there are a few problems in the book that try and get you to get the derivative values by trying to get you to draw and do a little approximation. There's still value in the graph, and in your book they've got a nice grid set up, but I really want to jump in and start talking about the functions as equations. So let's start off with a problem. Let's look at the function f of x equals x squared plus 3x minus 1. And we want to find the slope of the tangent line to the curve f of x. Let's do this at x equals 2. So my a value in this problem would be 2. Okay, so I've asked this whole question, right? Given this function, here are our directions. The very first thing I want to point out is the notation. That if you are given this function with these directions, an alternative, a synonymous set of directions would be find f prime of 2. Here, we're spelling it out. Here, starting to embrace the notation. So that's definitely something. The biggest thing for this section is to get used to this definition and using this definition. But we also want to start to use this section as to get all those little reminders. So we'll definitely at the end talk a little bit more about applications and units. But for right now, just starting to make that connection between this full statement and the notation. Find f prime of 2. Well, we've got notation to do that, but when you find this value, what does it represent? What does this answer represent? It represents the slope of the tangent line to this curve at x equals 2. Okay, so how do we do that? Well, I'm going to follow my definition. F prime of 2 would equal the limit as h approaches 0 Don't forget this limit notation, everybody. I know we're just getting into this, but that is going to be one of my first little nitpicky points. If you don't have the limit, you're not getting the tangent line, you're just setting up a secant line. So again, embrace the notation, don't fight it. So we've got our limit. Being completely literal, I'm getting f of 2 plus h minus f of 2 all over h. But now, let me embrace this. What is f of 2 plus h? This was originally given in my problem. So f of 2 plus h, replace all x with 2 plus h. 2 plus h squared plus 3 times 2 plus h, and the minus 1 is still there at the end. I could plug this in my formula, but I'm just going to do a little arithmetic, clean this up on the side. 2 plus h squared, foiling that out, 2 plus h will give you 4 plus 4h plus h squared. Here, just a little distribution will be plus 6 plus 3h, and we still have the minus 1. And now, I have a couple of like terms here. Have an h squared, just my habit, I'd like to keep that in front. A 4h and a 3h becomes a 7h. A 4 plus 6 minus 1 gives me a plus 9. So that f of 2 plus h, a lot of little work to get there, but that's the simplified version. That's as good as it's going to get. Minus f of 2, well, just for room, everybody, I'm going to squeeze that in up here. F of 2, that's much easier, right? We're much more accustomed to just plugging a number in for x instead of this type of expression. But by the way, everybody, that should have been something that's come up a little bit before in pre-calculus classes, and maybe you weren't the best at it. Here is where we're going to need a lot of practice to embrace this notation. But f of 2, that shouldn't be bad, right? Just plugging that in. 2 squared is 4, plus 3 times 2 is 6, minus 1, so I get 9. So I got all of this is this, so that one here, minus f of 2 was minus 9 all over h. Now, let's finish cleaning this up, right? Limit. Actually, I should have pointed this out right off the bat. I'm very sorry. Right off the bat, we say our first step when taking limits is to plug in the value. And then we only do all that extra manipulation work if we get into trouble. But go back right to the very definition we started with. If you're setting this up correctly and you let h be 0, well, this is 0, a plus 0 is a, so you get f of a minus f of a, which is 0, all over h, which goes to 0. So this definition is always setting us up for a 0 over 0. We can confirm that right here. H is 0, f of 2 minus f of 2. Doesn't matter what f of 2 is, you're subtracting the same thing from itself, so that's 0, all over h, 0 over 0. So I'm very sorry about that. I should have pointed that out right off the bat. Any of these derivative problems, they are limits, but if we set them up correctly, they'll always be 0 over 0, so they're always going to need some manipulation. Well, how do we manipulate here? We use the equation. That gave us this kind of algebra. Again, I could have done all of this work inside of this limit, and we've seen things like that before. Now, I could try plugging in h as 0, but I get 0 plus 0 plus 9 minus 9, 0 over 0. Still 0 over 0. We kind of mentioned this when we did our limits. These problems with that h in the bottom, that's always going to need to cancel so we don't get into trouble. So I still have to keep manipulating. Well, what can I do? Hey, like terms, plus 9 minus 9, they cancel. And now that that's all that's left, now I can individually cancel one h from each, divide both by h, or factor an h out so that it cancels. It's whichever way you prefer. But now we're ready to finish this first problem. All we're left with is h plus 7. And now when I let h go to 0, I get a final answer of 7. So f prime of 2 equals 7, meaning the slope of the tangent line to this curve at x equals 2 would be a value of 7. I tried to intentionally pick a parabola that's not easy to visualize, but if you draw a parabola, you'd have to work a little bit to see where the vertex is, but you'd have this nice upright parabola, and at positive 2, you'd see a very nice positively sloped tangent line. Very, very roughly, this curve would be something like this. So again, by the time you get out here to 2, you'd have a pretty steep tangent line, and that's exactly what we're seeing here. But realize, I never needed to draw this picture. That when we have the equation, this definition will be what we're relying on. That's what we used to get this answer. Okay, that's still only one problem, and it's still leading us to several big issues. Because now as I flip to our next note page, let's realize a separate issue. If I had that same exact function, x squared plus 3x minus 1, and now I asked you to find f prime of 3, you would have to start all over again. All this work. Now you'd have to go back to here. You'd have f prime of 3 would be f of 3 plus h minus f of 3 all over h. You'd have to do f of 3 plus h. 3 plus h squared plus 3, quantity 3 plus h minus 1. You'd be repeating a lot of the same work. It would be similar, but you would have to do it all from scratch. So, one of the first things we want to point out is that while that was the basic derivative at a, what we can do instead, and this is definitely a better way, let's not start off right off the bat by finding f prime of 3. Let's hold off on that. So we're waiting on this. We will come back and answer this, but let's actually start by finding f prime of x. One of the first big things we want to realize is that when we have an original function, we can then find its corresponding derivative function. Now, there's a few technicalities we should certainly realize. Every aspect of the derivative, how can you draw a tangent line? Well, the first thing you need is your function needs to actually be there and needs to be connected. So we'll come back and talk a little bit more about the properties of the derivative, what does it mean for a function to be differentiable, and just, some more of the basic properties that go with the derivative. We'll save that for 2.2, and that'll be a part of our second test. Like I said at the beginning, I really want this last unit for our first test to focus on this actual definition. But it's good to realize that this would only make sense if there was actually a point here. If there was a big jump from here to here, you can't draw this. If there was a vertical asymptote at this point, you couldn't draw the tangent line. If there was an open circle or a jump, you couldn't draw the tangent line. So this aspect of tangent line relies on continuity that we've already established. Okay, so now back to this. And now back to that second point, that this is a separate function. That the idea of a function is simply you have an input and you can find an output. And in our traditional function, we think of that, I give you an x, you give me a y. I give you x is 0, you plug it in and get y is -1. Or on the previous page, you had an x value of 2 and we found out that y was 9. So we're very familiar with that, but now we have to realize this is also a function. You're still inputting an x, but the output is no longer the y, the output is the slope of the tangent line at that point, at that particular x value. And again, these are functions. The x is enough. I don't need the xy pair. The x is enough to tell us where we need to look on our function. Okay, now we put all this together. So now, f prime of x, We had the notation for f prime of a. It's the same thing for f prime of x. We'll do it a little more generically. It's still a limit as h approaches 0, but instead of f of a plus h, we'll do a generic x plus h minus generic f of x all over h. You might quickly look at this and say, well, what did he change? I didn't change anything. I just changed a to x. Just pointing out that we don't need a specific a value. We can do this generically for x. And then after the fact, we could use the new function and find the slope at any given a. So if that sounds confusing, just hold on, everybody. Let's find the f prime with this original f. Let's find the derivative function, and then we'll verify what we just did on the other page and also come back and realize how this will be more helpful than just this. So f prime of x, well, just like before, I need f of x plus h, and I'm going to do this off on the side. I really strongly encourage that here, everybody. These problems can be a little lengthy, and there's a lot of notation and stuff floating around. So sometimes it's nice to just do a little scrap work off on the side. What is f of x plus h? Well, just like before, it's the quantity x plus h squared plus 3 quantity x plus h minus 1. And this is what I was saying, everybody. You have to get used to this. Every definition of the derivative problem we do, we're going to need to establish this notation right off the bat. And for a lot of people who struggle using the definition, very often this is a common spot where they goof. Let me show you something that's not correct. People who think f of x plus h is x squared plus 3x minus 1 plus h. They see the plus h here, so they just stick a plus h at the end of their original function. That's not how the notation works, everybody. This would be quantity f of x with the plus h out on its own, and that's not helpful. That does nothing for us in this problem. So what is the correct way? It's always, just like we do with our numbers, whatever is inside the parentheses here replaces the x and preserves all the same original relationships. So x squared became quantity x plus h squared. Not x squared plus h at the end here. That's not it either. The whole x was being squared here, so now the whole quantity x plus h is being squared. 3 was being multiplied by x. Well, now 3 is being multiplied by the whole quantity x plus h. Not 3x with a plus h. We need that x plus h in parentheses, so all is being multiplied by 3. The minus 1 was just floating along, had no x, so the minus 1 is still here. And now, just like we saw with the a plus h notation, if you just try plugging in h is 0, you're going to get 0 over 0. If you try applying the particulars of the function using the equation, the same thing is going to happen. So, but for this first one, I do want to put all this in my notation. I'm going to have x plus h squared plus 3 quantity x plus h minus 1. All of that is the f of x plus h. So all that is going in place this minus the original f of x. So that's x squared plus 3x minus 1 all over h. I have my limit as h approaches 0. Do you notice I actually have a small mistake right now? Here's a second common mistake with the definition of the derivative. Particularly when our functions have more than one term, we have to realize this minus f is minus the entire function f. So if there's more than one term, that set of parentheses is going to be necessary. And now one more time. Some people like to use this as a check. Is this set up correctly? If this is set up correctly, we'll know it because we're getting 0 over 0 if I try and plug in 0 for h. 0 for h, x squared. 0 for h, 3x minus 1 minus that exact same thing. So we get 0, and there's h, which goes to 0, 0 over 0. Now, once you get a little practice with this formula and plugging in, I think we can skip over that little step and recognize we're not skipping any steps. We're still applying the same limit techniques we always have, but we just recognize we're always going to get 0 over 0. So that we can immediately move into the manipulation part next. And manipulation here will be very similar to what we had on the other page. And that's what I was just saying over here a moment ago. How are you going to manipulate this? How are we going to get to simplify? We're going to need to get rid of all these parentheses. So that's, again, as you get a little more practice, some people don't write this in here. They've already did this off on the side. Let's finish cleaning this up. What is x plus h squared? X plus h times x plus h. You'll end up with this. I know I've said it a couple of times, but it's worth reminding. Don't just square the x and square the h. You have to FOIL this out, x plus h, and that's where I'm getting this middle term. And even here, just to be careful, some people get xh and then hx. It is the same thing, everybody, right? You could easily flip them both into xh's, so that way you see their like terms and combine them to 2xh. Here, distribute the 3 plus 3x plus 3h. The minus 1 is there. Distribute this negative. Again, in the derivatives, we have not simplified enough until this h is gone. So we're off to a good start, but we still have got a lot to do. What comes next? Well, before I even look at the denominator, go back to the numerator. Notice we've got a lot of like terms. And not just like terms, they cancel. Positive x squared, negative x squared. Positive 3x, negative 3x. Minus 1, positive 1. So now collecting everything that's left and realizing what's left, there are no more like terms. So it feels like we're a little stuck. But now we're in that good situation. Yeah, there's nothing more I can do up here, but now all these terms have an h. I mean, nothing as far as there's no more like terms. Nothing else combines up here. Don't start going too far. Don't make this a 4h squared. These are not like terms. These don't combine, right? That's as far as you can take this expression. But what we can do from here, now we notice they all have an h. So I could divide. Again, you can't pick and choose and just divide one. You divide all 3 by h and all 3 would clean up. Or you can look at it as factoring 1h out, and then you could cancel that 1h. That's one of the advantages with the derivative problems. When we had 0 over 0 with random limits, we had no idea exactly what needed to be done. We needed some experience. We had some guidelines to say, okay, this looks like a factoring. This is a conjugate. This is a clean up the fraction. But some of those ideas still kind of overlapped. We'd use the conjugate, but then we'd have a little bit of factoring that needs to be done. So all that really needed some practice and experience. But now that we're getting into the derivatives, this is just such a common outcome. Get it set up, good things happen, that bottom h cancels, and now we could finish and take the limit. H goes to 0, just the h, so the 2x plus 3 is left behind. So now, instead of just having the derivative at one single value a, now you've got the derivative function. So now, instead of doing all of this work over and over again as we get different values for a, well, this is what we did when a was 2. But now when a is 3, we got to start all over again. Look at this. Now that we've got the derivative function, what is f prime of 2? We use the function notation. We don't plug 2 into f of x. We plug 2 into f prime. That'll give me 2 times 2 plus 3, and that gives me 7. Not a coincidence. Sorry. Plug the 2 in here. 2 times 2 plus 3. 4 plus 3 gave me 7. That is not at all a coincidence that what we have here matches what we did over here. And now realize, let's just keep going. Now you want f prime of 3. Look at how fast. Now that you've got the derivative function, you just plug in here. We'd get 2 times 3 is 6 plus 3. So the derivative at 3 equals 9. What about the derivative at negative 1? Well, I'd plug negative 1 in. 2 times negative 1 is negative 2 plus 3 gives me positive 1. What is the derivative at x is 0? Plug in 0 when you get 3. Now that we have the derivative function, now we could find the slope of the tangent line at any x value we choose. I mean, again, there will be some limitations. There will be some functions, have a couple of discontinuities, have a couple of spots where the derivative doesn't exist, but this is the big picture. Starting with an original function whose output is just a y value on the curve, now we've got a whole new function whose output is the slope of the tangent line. One more little thing to finish. The book, the homework, really focuses a lot on the derivatives and the slopes, but now realize this is going to be a very common question. I want us to see it once now, and then we're going to see it a lot as we move through the rest of chapter 2. Let's find the equation of the tangent line to f of x. Let's still use that same f of x one more time at x equals 2. There's your problem. Find the equation of the tangent line. Now, a lot of you, when I say equations of lines, a lot of people, the first thing they remember is y equals mx plus b. But I'm going to encourage us to remember this formula, the point slope formula. Here, you need specifically to find the y-intercept to use this. So this is a very useful equation when we graph, when we think of straight lines. It's already solved for y, but this will be just fine for us, everybody. If we want the equation of the tangent line, this will allow us to use any xy pair, and we'll also need the slope. So how would I get the xy pair? Well, you have the x coordinate. We get the y by plugging into the original function, which was already given. So I'll do that quickly. That's 4 plus 6 minus 1. So we get the xy pair is 2 comma 9. The slope, well, we're certainly going to take advantage that we've already done the hard part. If we were starting this as a fresh problem, there would be a lot of work to get this derivative function. But we've already got it, so I'll take advantage. I mean, and technically we already had the slope, but just pretending that this was a fresh problem. The original function, we use that for the y. Now we need the derivative function. We had to work hard to get that, but now that we've got the derivative function, now we can plug that same x coordinate in here, and that would represent my slope. And now I could finish with this. Y minus the y coordinate equals m times x minus the x coordinate. And to be perfectly honest, everybody, I know the book, when they ask these questions and you check your answer in the back, they will put that into y equals mx plus b. It's not that hard, right? Distribute the 7, add the 9 to the other side. It's not that terrible. You'll get 7x here, minus 7 plus 9, you'll get y equals 7x plus 2. But for any test quiz, I have no problem at all if you just leave your answer just like this. And every once in a while, we'll have some ugly values. It won't be so easy to find b or to resolve this equation. So again, I'd have no problem if you left your answer like this. Okay, so we've said a lot so far in this video. As we move into part 2, I really want to put most of our focus on practicing with the definition of the derivative formula, and then get back to a few of those reminders. Just as this, we're seeing a little bit with the whole tangent line here, but we'll see a lot more of that with chapter 2. Same thing with the applications and the units. We'll just get a taste of it here, but we'll really see a lot more of that going on. So one more time before we move to the second video, I'm focusing so much on the definition of the derivative because that's what you're going to be responsible on the first test. I want to hit these other notes so we start to make the connections, so we'll have a good start as we continue into chapter 2. But right now, the definition of the derivative is definitely your first priority.